Thank you, Rachel. There are two clickers up here, and I wonder which one. It's this one. All right. Okay, so before I start talking about tidal energy, I first want to tell you about the tide. And so to do that, I invite you on a little trip. We're going to go up to this bay in Alaska. And here, we're going to sit by this bay all day and watch the tide come in. And you might be thinking, how relaxing, I'll go get my book, it'll be sunny. So as we watch this, I want to tell you what I see. I see gallons and gallons of water pouring into this bay, think about how much energy it takes to bring all that water in. I see that dock rising up and a landscape totally changing. So when I look out at the ocean, all I see is power. And so how does the tide work though? We have the moon and we have the earth, and the moon exerts a pull on the earth, and since the ocean is fluid, it can react to that pull. And so the side of the earth that's closer to the moon gets pulled, and the sides that are farther away get pushed as if you're pushing a balloon, and it elongates. So you have two bulges on either side and smushed in the middle. And then the earth rotates every day, and so you pass through 2 high tides and 2 low tides every day. This is a really cool force of nature. It happens every day, twice a day, and we can predict it indefinitely. So what if we could make energy from that force? So as the tide pushes water from one place to another, it creates speed. The water moves, it creates a current. And that current can be used to power a turbine, much like a wind turbine is powered by the wind. So this is a form of renewable energy technology, producing energy from the tides. And like solar or wind, this energy is not generated from fossil fuels. So that means it's renewable indefinitely. As long as the sun is shining and the moon orbits around the earth, we can create power. Also, this technology does not emit CO2. So that means that the carbon dioxide that's creating ocean acidification, this is a direct solution to that problem. But tidal energy has some cool benefits that maybe aren't present in wind or solar. To start with, as I said, tidal energy is extremely predictable. We know what the tide is going to look like years in advance. The next benefit is that water is much more dense than air. In fact, water is 1,000 times more dense than air. So if the wind was blowing at the same speed as water was moving, we could make 1,000 times more power. In reality, we tend to just make tidal energy from slower moving currents, but there's a lot of potential there that is maybe not there in air. And the second benefit is that while wind and solar are often best located in very rural locations, tidal energy can be made right near our coastal cities, like our beloved Seattle. The energy can be generated right where it's needed in our cities. Okay, so as I may have alluded to, tidal energy is not yet a full-grown industry like its peers, wind and solar. In fact, there are a lot of different potential designs that are still being considered. You have things that look like a windmill underwater, but perhaps have 2 blades or 10 blades, perhaps have a shroud surrounding the outsides of the blades, or move in a different direction, like a lawnmower blade. And all of these different devices might be useful in different locations, or they might have different design specifications, like they're best in deep water or shallow water, they're best in faster moving water or slower moving water. And so these are all things that we use to choose which designs might be best in a given location. But I want to add another thing to our list of potential design specifications. I want to add, how do these devices impact the environment around them? So if you put this big giant piece of steel in the water, by definition, it changes the environment it's in. It literally takes energy out of that environment. So every way of creating renewable energy takes energy out of the environment. But how does this one do it in particular? and what kind of environmental impacts can we mitigate for? So the one that I'm really interested in is how do these devices impact marine mammals and how do they impact fish? So let's talk first about this turbine, which is a two-bladed turbine that's proposed to have 16 meters in diameter for each of those two sets of blades. So they're big things in the water. And if you are a little harbor porpoise in the Puget Sound, a common marine mammal here, that looks pretty big. It looks a little intimidating. So how would you react to that device in the water? So currently in the US, there aren't any devices that are in the water long term. And so how marine mammals react to those devices is still kind of a question. We don't really know. And if I had to make the best way of deciding how these animals reacted, I would, observe the devices with marine mammals or fish and see what happens. But nobody's gonna let me have a permit for that if I think they might, hurt the marine mammals. And so we don't have any devices in the water. So we're in a bit of an infinite loop where we can't put devices in the water because we don't know what's gonna happen, so we can't put devices in the water. And so we need some creative solutions to figure out how do we get out of this loop and actually create this cool renewable energy technology. So, wait for it, okay. Here's an orca and a smaller tidal turbine. And I want to tell you a couple of the potential environmental impacts. So the first one that might impact this whale is the noise that this tidal turbine generates. So as the gears turn inside of it or the blades move through the water, that turbine might create a sound. And the sound is something like you're walking, down the street in downtown Seattle and you see a construction site to your right. And you were gonna go to a store down there, but the construction's kind of loud and putting some dust up, and so maybe you don't go to that store. But if you really wanted to go to that store, you'd probably still go there. But maybe, so there are subtle behavioral changes that could happen from sound. And this really depends on the frequency the sound is and how loud it is, and all of those are variables that we can change as we're designing these tidal turbines. So the second impact I want to talk about is the risk of colliding with one of these turbines. And when you saw that giant turbine with that tiny harbor porpoise, that's probably the first thing that you thought of. And for a lot of people who permit these devices, that's also the first thing they think of. What happens if it hits, that spinning blade hits a marine mammal? Will it kill it? The first thing I want to say before we dive into this topic is that these animals are incredibly smart. They are naturally able to avoid objects underwater and have great sensory capabilities. And the second thing I want to say is that when we think about the environmental impacts of putting a energy generating device in the water, we're really considering, instead of considering turbine or no turbine, we're thinking turbine or coal plant. We're thinking turbine or dam that's taking away the salmon that these orcas eat. So every way of making energy has environmental consequences. And my research aims to make sure that the ones that we propose are better than the ones that we're trying to replace. And so what I want to talk about when we talk about potentially hitting a marine mammal is a worst case scenario. Once again, these devices are moving in relatively slow currents and tend to move about 8 rotations per minute. So if I do my arm like that, it's pretty slow. And so when we talk about injury from these devices, it's often a soft tissue injury that we're thinking. We're not thinking it's going to break the bones or rupture the muscles. We're thinking a soft tissue injury on the outside of the skin. Okay, so I told you before that we can't just go out and hit marine mammals with turbines, right? That'd be bad. So we need some creative solutions to get around that. And the way that I want to do that is by combining biology and engineering. So let's first take a trip to biology. So the biologist version of myself asks, how do marine mammals respond to trauma? How does their skin break and rip and tear? What happens if you push on it? What happens if you pull on it? And so first question, what happens if you pull on marine mammal skin? And so I answered this question by first getting a phone call that says a marine mammal has washed up dead, specifically a killer whale, on the shores of the Puget Sound. And I go out with my knee-high rubber boots, my elbow-length gloves, a foot-long knife, and I cut a piece of tissue out of that animal. So I cut the skin and the thick, fatty blubber layer down to the muscle. And then I separate the skin from the blubber, and I cut it into 2 smaller subsamples of some of skin and some of blubber. And then I test them by pulling on them. I pull on them with a machine that records the force as I pull. And so from this test, I get to understand 3 things. 1, how elastic is the material? How much force does it take to pull on it? And the second is how strong is it? How much do I have to pull on it before it breaks? What's the highest force it can withstand? And 3, how much can it stretch before it breaks? So when we test these 2 different materials, we find a couple of differences between them. So I'm going to illustrate them here on my block of tissue. We have the skin is in black and the blubber below it in pink. And the skin is much stronger, but it can stretch further before it breaks. And then the blubber is squishier and more malleable, kind of like, but it can't be pulled, or it stretches less before it breaks. So let's think of this as a piece of Jell-O, super malleable and squishy, but maybe can't be pulled much before it breaks. And then a sheet of rubber. We're gonna put a sheet of rubber. So let's imagine that we put a block of Jell-O and they put a sheet of rubber over it, and then let's just do like a gentle karate chop on that. Hi-ya! And then perhaps the blubber, doesn't break under it. But if we were to reverse that and put the Jell-O on top of that piece of rubber and karate chop that, softly, the Jell-O would break. And so this is cool and illustrating how the skin acts to protect that underlying blubber layer. And that's really important for how the animal responds to, getting hit by anything, whether it's, another animal or anything else in the water. So the next question I ask is, what happens if you push on this tissue? And so I have a piece of tissue with the skin and blubber still connected, and I take a little rigid ball and I push into it, and I find out how much can you push on it before it breaks. And so here I want you to think about your own skin and how squishy and malleable it is. So if you take your thumb and put it into your cheek, you can squish that all around and you're not damaging anything. And so that's pretty cool. It's really changeable and movable without damage. And so this helps me understand the role of the blubber more. So the blubber acts to be able to be squished and moved around and allows a lot of pushing into the material without breaking. The other thing that we find with this test is the part of the tissue that's most vulnerable. So when you push down with that little ball, you can see that the first thing that breaks is the layer between the skin and the blubber. So I'm going to show you here, the most thing that's stretched is that layer, is the bottom layer of the skin, versus the top layer of the skin is less stretched, right? And so we see the most damage that happens at the interface of the skin and the blubber. Okay. So now we've concluded the sort of biology version of myself, and the engineer version of myself takes all of these sort of, measuring in terms of squishiness and elasticity and Jell-O-ness of materials and turns it into math. Okay, and so with that math, I can create a computer model that simulates a blade striking a marine mammal. So computer model, this is a simplified computer model, and you see the pink is blubber, lots of blubber, the black is skin, and the gray is a blade. And what you're seeing here is the whale model cut in half, so you're seeing the inside of a whale. And you can watch as the blade hits it. There you go. Okay, we'll watch it here. There it goes. Okay, so it pushes in, but what you see here is not enough deformation to break the skin or break any part of this animal. So it can squish a lot without breaking it. And so this is like a slow speed blade, right? So slow speeds, they're not going to break. So what we can do is we can ramp up the speed of this blade until it breaks, right? So, oh, there's the video now. Okay, you can see it again, it squishes around, the blubber's all jello-y. Okay, so if we ramp up the speed until it breaks, this is an example of what it looks like when the material actually breaks. So here, all of that gray is tissue, both skin and blubber. The black is the blade, and that little bit of white is a damaged area. So we sped up the blade, and we can see that the damaged area is that same area we predicted is under the bottom layer of the skin, between the skin and the blubber. And so if you imagine what that injury looks like, if the outer layer isn't broken, that looks like a bruise, right? It's a lot more healable, it's a lot more recoverable. So we can sort of say this injury is recoverable, and maybe it's not a bad thing for the animal. So with each different blade design or each different turbine design, we can evaluate what's the speed at which this blade would hurt this animal. We can compare those sorts of things. So when we look back at this picture of a whole bunch of different potential turbine designs, we can say, okay, we can do that two-bladed design as long as it's not spinning too fast. We can do that shrouded design, the one with the sort of shape around it, because as long as we don't put it in waters too fast. And so we can make decisions that allow us to add our environmental specifications to our design specifications. And this is a really cool opportunity, since this industry is still emerging, to make decisions based on the environment. So ultimately, I hope to be able to add the tagline to this technology: no marine mammals were harmed in the making of this renewable energy. So thanks so much to Engage and Town Hall, and I'd love to take any of your questions.
How much can you extrapolate the killer whale to other tissues from other species? And also, your models seem to imply that the blubber sample is stationary. When it's in a water column, it will respond downward. And so, how do you model that?
Okay.
I mean, the mass of those blades has got to be 5 times the mass of a 300-pound whale.
Yeah, the first question is, how did the other animals compare to killer whale tissue? I have tested 5 different marine mammals that range in size from, the tiny harbor porpoise and harbor seal up to the killer whale, and they're very different. And the killer whale is the only data I showed today, but we probably need multiple models to evaluate each individual species, depending on maybe different locations that you're interested in looking at. The second question is, how does the blade transfer momentum to the whale, and how does the water around that impact? And in my models, I have basically tiny little springs that act like the mass of the water below the whale. And so when the blade comes down and pushes on the whale, those springs give the force of the water back up. And so we're taking that into account. Different blade designs and turbine designs have different masses. Like if I model a tiny animal, like a seal, that tends to be like pushed way out of the way, but the killer whale tends to actually stop the rotation of the blade.